TrueGrid is a 3D mesh generator and preprocessor used by engineers and scientists to build a computer model as the first step in a computer simulation. In this video, you will see 3 example hexahedral brick element meshes built using TrueGrid. They represent 3 important areas of computer simulations: structural analysis, biomechanics, and computational fluid dynamics. In the last portion of this video, you will see a demonstration of the unique technology in TrueGrid called the projection method. A simple but significant quadrilateral shell mesh is constructed in 4 steps. Each step represents one command issued by the TrueGrid user. The method used to form this quadrilateral shell mesh is identical to the method used to form all meshes within TrueGrid. In this example mesh, created using TrueGrid, we have a structural component consisting of 26,463 nodes, 21,154 hexahedral brick elements, and 91 prism brick elements. This small number of prism brick elements were needed near the overhang because of some of the intersecting surfaces were tangent to each other. The next example of a TrueGrid mesh comes from the biomechanical field. It is an all-hexahedral mesh of the human left and right femur, left and right ilium, and the sacrum. This model consists of 106,393 nodes and 87,105 hexahedral brick elements. The geometry for such a model usually comes as a CAD geometry or as stereolithography. TrueGrid is ideally suited for biomechanical problems because of its unique technology called the projection method. Here we have 17 surfaces, each with a different color, imported into TrueGrid from a CAD system. These surfaces form half of the outer shell of a jet engine nacelle from a large commercial aircraft. These surfaces are used as the boundary surfaces for the mesh of the air around the nacelle. The fluid mesh formed by TrueGrid around the nacelle consists of 229,185 nodes and 213,088 hexahedral brick elements. Notice that most of the elements have nearly right angles. Near orthogonality in the mesh is critical to getting an accurate computational fluid dynamics simulation. One of the most important features in this mesh is the boundary layer. In the boundary layer, the elements are very thin. This is because the shearing of the fluid takes place primarily along the boundary, and a thin mesh is needed in this area for an accurate simulation. But it is also important that the transition from larger elements to thin elements are done gradually. As we zoom in, you can see layer after layer of thinner elements until we reach the smallest elements at a factor of 4,000. This boundary layer was calculated by TrueGrid using a 32-bit computer. Much higher factors can be achieved with TrueGrid on a 64-bit computer. This is a demonstration of the basics of the projection method. We start with a simple block-structured mesh formed of 2 boxes. The larger box will be projected to a larger cylinder, and the smaller box to a smaller cylinder. I'll show those cylinders. The first step in this process is to move or shape this smaller box so that it aligns itself with the smaller cylinder. The next step is to project the larger box onto the larger cylinder. You'll see here that the nodes on that larger box have now been moved precisely onto the cylinder. I'll remove all the surfaces now so we can focus on the mesh itself. The next step and final step is to project this smaller box onto the smaller cylinder. And that completes the demonstration. It should be noted that the nodes that follow where the two cylinders intersect are projected precisely to the intersection of the two surfaces, the two cylinders, and that's done automatically.